So to get things started, we have Piers Buchanan from the University of Liverpool, who's going to talk to us about the fingerprints of nitrogen and nitrogen limitation. So over to you, Piers.
Hello, hi everyone. Good morning if you're in the States, and afternoon, evening, wherever you are. So I'll just share my. Okay. Right, as Adrian said, my name is Piers Buchanan, for those who don't know me, and today I'm going to tell you a story about how the properties in the Twilight Zone may fingerprint growing signs of nitrogen-limited phytoplankton in the coming decades and the future. So this work was done in collaboration with Claire Mahaffey and my mentor Alessandro Talibue here in Liverpool, and also involved collaborators in Paris, Olivier Almont and Lauren Ball. So the way I will structure this talk is I'll spend quite a lot of time on motivation out of the 20 minutes, just to kind of broaden the perspective and maybe invite some discussion afterwards. And I'll spend a short amount of time on results and then quickly finish up with some brief implications. Let's get started. So climate change is happening rapidly. All right, so I really like this figure because it brings into sharp focus the changes that are occurring now and how rapidly it's occurring. So over the last 800,000 years, you're seeing on the x-axis these what are considered rather dramatic swings between glacial maxima, where atmospheric CO2 is roughly 180 ppm, to these mild interglacial periods. And these are considered quite dramatic climate changes in themselves. And then in the blink of a geological eye, you see the rapid rate of carbon dioxide concentrations increasing. Right now, we're at roughly 412 ppm. And we could end up anywhere between this green and yellow dot by the end of the century. So extremely rapid climate change. And with this, there are some known knowns. So we know that the climate is warming, and this warming, 90% of it is going into the ocean. And this shows mean surface sea surface temperature. This plot is showing mean sea surface temperature over the historical period into the future based on a model scenario. It's the RCP 8.5, and just ignore that grey box there. Another known is that the circulation is changing. And exemplifying this is this recent paper by Jean-Baptiste Sally, showing everywhere that's red an increase in stratification in the picnic line. The picnic line being the place in the ocean where the density gradients are strongest. So this tends to be in the mesopelagic or the Twilight Zone, right? Relevant for this crowd. So the ocean is stratifying, but also what's happening is there are also changes in the overturning, so the AMOC slowing down or predicted to slow down, and this will have implications. Right, so in terms of biogeochemistry, what these two known knowns, I'm calling them, will do is for warming in terms of biogeochemical rates, it will increase them. If we think about biogeochemistry and the community in terms of the whole community rather than individual taxa, which has this skewed bell-shaped temperature optima, and then with additional warming, actually the rates decline. If we think about things in terms of the whole community, then warming tends to increase microbial rates. Now with circulation change, what I was talking about with AMOC slowing down and stratification, this tends to reduce nutrient supply to the surface ocean. Now, both of these together tend to work synergistically. And so we have pretty high confidence that nitrates in the surface ocean will decline, and other nutrients. So this is a figure from a recent CMIP6 synthesis article by Lester Kwiatkowski, showing the multimodal mean trends in nitrate at the end of the century compared to the historical. And everywhere where the models tend to agree, which is where nitrate tends to decline quite strongly, stippled in the dots. So you notice in the subarctic, the Arctic, in the tropical and eastern boundary upwelling areas, and in the Southern Ocean, nitrates declining. So we have relatively high confidence that this is occurring because we know that warming and the circulation changes are occurring. what this might mean is that we may be going from a situation where currently we have this picture in terms of the major limiting nutrients. Nitrogen, where nitrogen is most limiting to primary production, is in the blue, and where iron is most limiting to primary producers is in the red. Now, these are hard-won measurements, right? They're shipboard nutrient amendment assays. So each dot here is worth a lot of money, and what they're showing is that generally nitrogen is limiting in the low latitudes, in the subtropical gyre systems, in the tropical Atlantic, whereas in the upwelling areas, in the Southern Ocean high latitudes, iron is the main player. And so there may be a situation in the coming decades in the future whereby some of these red dots, which represent iron-limited regimes, become nitrogen-limited. This would be synonymous with the expansion of the gyre biomes that I'm sure all of us have heard something about. So this paper by Polovina showed that for their study focusing on the North Pacific, you see this purple area is delineating the low productivity nitrogen limited gyre ecosystem. And as it, under an RCP 8.5 scenario, climate change scenario, this gyre system expands. And what you also notice is that this equatorial tongue of high nitrate, high productivity water that comes up in the equatorial and East Pacific also shrinks. While we're more sure about the nitrate declining, we're less sure of what will change in terms of phytoplankton productivity. So even though there may be this, we might think that there may be this increase in nitrogen limitation of phytoplankton, actually net primary reduction is dependent on so many other things, right? So it's dependent on different nutrients, iron, phosphorus, silicate. It's dependent on temperature, as taxa change depending on the temperature thresholds. It's dependent on top-down pressures, grazing. And so our understanding of the response of net primary production is much less certain. And this is exemplified by this study by my mentor here, Al, looking at the recent CMIP-6 simulations in net primary reduction and breaking these down per region. And everywhere outside of the Southern Ocean and the North Atlantic gyre, we see that the multimodal mean trend and the intermodal spread of these predictions intersect with zero. And so there's actually very little confidence as to what's going to happen with net primary reduction in the future, according to our models. And if our models can't, even though they're quite simple with biogeochemistry still, if they're showing this degree of divergence, then we have a problem, right? So we need to find a way to monitor these changes going forward. And so the challenge, therefore, is to constrain our projections via a sensitive means of detection. And the way I'm proposing to do this is using nitrogen isotopes. There's a lot more in this study than I'll go into, but I'm just going to focus on this part of it. So in a system where we have nitrogen is replete, so nitrogen upwells, there's lots of nitrate in the surface ocean, phytoplankton undertake what's called luxury uptake of nitrate. So they take up more nitrate than they need, and then they exude some of that nitrate back out to the environment. In a system whereby that is nitrogen limited, this actually doesn't happen. So nitrate take up whatever they can get, and they use whatever they can get to synthesize organic matter. This matters for the isotopes because in a situation whereby there's, so generally there's more light isotope 14N than 15N, and because the phytoplankton cells prefer to take up the 14N, they exude the 15N back into the environment. Now, over time, what this does is it increases the amount of 15N that's available in the upper ocean. And if you can imagine a water parcel that upwells in the tropics and then moves out laterally towards the gyres, you can imagine an accumulation of 15N in the upper water column. And due to this preferential assimilation of 14N, more of that 14N has to go somewhere, right? It will be removed from the upper water column through sinking and remineralization in the tropics. Over time, this means that more 15N will end up in the subtropical dry biome. In a situation where nitrogen is limited in the surface ocean, this preferential uptake of the 14N relative to 15N doesn't occur. So phytoplankton just take up whatever nitrate they can get, they assimilate whatever they can get, so roughly equal measure these light and heavy isotopes are taken up. And that means in roughly equal measure, these light and heavy isotopes make their way into the subtropical dry biome. And this will be, all you need to remember from this is that if there's nitrogen limitation, then in a Lagrangian perspective, going towards the subtropical gyres, this will register as a relative decrease in the delta 15N of nitrate. So decrease in these isotopes means more of the light isotope is getting into the gyre biome. Right. So the hypothesis is that stands as this, right? So climate change is happening rapidly. We have some known knowns that warming and circulation changes are occurring. This will lead to nitrate declines. Now, whether this actually causes nitrogen limitation is something to be seen. But if that does occur, then the nitrogen isotopes will respond. And so in order to test this hypothesis and see how it plays out, we use the global ocean model, the NEMO-PSCUS, which has a complex nitrogen cycle and ion cycle, a very useful biogeochemical module. And we added the isotopes to this model. So we span it up for 5,000 years, got a relatively decent agreement with the current compilation of nitrogen isotopes we have for the ocean. And then use this to run, I'm just going to talk about two simulations that we did in this study. We ran a pre-industrial control simulation from 1801 to 2100, and then we branched off at 1851 and ran the climate change scenario from under the RCP 8.5. And we looked at the difference between these two simulations just to detect changes and see what happened, right, in relation to the isotopes. And so what did we find? We found that in the low latitudes, more generally, bioavailable nitrogen declined, much like we saw in the multi-model mean synthesis by Lester Kwiatkowski. So you can see that in the blues, bioavailable nitrogen has declined. And what I mean by bioavailable nitrogen here is ammonium and nitrates. This model simulates both. What happens thereafter is that net primary production declines in many areas of the low latitude ocean. So in this simulation, what we're getting is nitrogen limitation of these ecosystems. So then the blue areas are where net primary production of phytoplankton is declining. You can see that it's very strong in the tropical Pacific and Atlantic. And then this decline in the low latitudes is more than compensating for the increases in the high latitudes that are expected with climate change. So a net decline of 5% in primary production. And as per our expectation in that hopefully clear explanation that I gave earlier with regards to the isotopes, we find that this delta 15N of nitrate does decline. Now, it declines specifically in the Twilight Zone. And what you're seeing here are everywhere where it's a greater decline than 0.2 per mil is shown in this figure. And the reason why I chose 0.2 is because this is our current measurement precision for measuring these shifts. And so you notice that in the North and South Pacific, the North and South Atlantic gyre systems in particular, in the Twilight Zone, these declines are actually very strong at the end of the century. And so our hypothesis about this more 14N coming in through nitrogen limitation seems to stand up. And just for those who are interested, this is a call about the Twilight Zone, so I'm sure all of you are interested. The Twilight Zone here that I'm talking about is anywhere between the top of the euphotic zone and roughly 350 to 420 meters, something like that. It's based on light in this study. Now, why does this occur? The reason it occurs in the Twilight Zone, and in particular in the subtropical gyres, is because these areas, subtropical gyres, happen to be areas where water accumulates. Again, from a Lagrangian perspective, if you're thinking about how water moves after it comes up in the upwelling areas at the equator and the eastern boundaries, it moves outwards and then it eventually accumulates in the, makes its way to the subtropical gyres where it then downwells. And so the products of biogeochemical processes that are occurring en route tend to make themselves most known in these areas. Moreover, the twilight zone nitrate concentrations are also relatively low. And this means that changes in the isotopes here are going to be magnified. But luckily, they're not too low because we can still measure these concentrations for their isotopes. So it means that these declines are not only able to be measured, well, they're able to be measured practically, not only in the model, right? To think about things in reality. So they're not only practically measurable, but they're also detectable. So we did a signal to noise analysis, much like a time of emergence, if people are aware of that, whereby the year in which an anomalous climate change signal emerges from the noise, here the noise is represented by, say, interannual variability. The year that this occurs, we don't denote the time of emergence of an anomalous signal. And so what you're seeing here in this middle plot is year 1900 to 2100, and then you're seeing the percent of the ocean where a anomalous signal has emerged. And I just want to draw your eye to the isotopes in the twilight zone of nitrate, the red line. You can see here that by the end of the century, 80% of the ocean has become anomalous for this variable, relative to, say, 50% for net prime production and a much later emergence as well. Same for nitrate in the photic zone, in the dashed, and the twilight zone in the solid line. You'll also note that the purple is the isotopes of organic matter. So for anyone who measures that, this is also highly detectable as well. So just to end quickly, I just want to say that in recent years, the physical variables have become understood to be quite sensitive to anthropogenic change. So in the twilight zone specifically. Here I'm showing you a figure from Sylvie and colleagues a couple of years back, not long ago now, showing changes in salinity that have been detectable and the year in which that signal, that anomalous change emerges. And so what you're seeing is the Atlantic, Pacific and Indian basins in this sort of bathtub style view from the side. And you can see that in many areas, in large areas of the ocean, the salinity changes due to anthropogenic activities are emerging quite early. And this is the same for temperature. In this case, the Southern Ocean, you're seeing the same sort of bathtub style representation on the side. You're seeing temperature trends that everywhere where there isn't these diagonal lines, temperature trends that overwhelm the interannual variability to be practically detectable. And so the reason why the twilight zone is much more detectable, these trends are much more anomalous and detectable than the photic zone is simply because of the signal to noise relationship. The signals might be greater in the photic zone, but the noise that they're dealing with is also much higher, whereas in the twilight zone, the noise is much lower. And in terms of biogeochemical variables, I'm talking about these physical variables, but for biogeochemistry, we have an extra component that lends itself to detection. And the reason why in this study, and I believe in others, there could be very detectable anomalous changes due to climate change in the twilight zone is because of due to this extra vertical velocity or vector we have, right? So through sinking and mineralization, the products of the euphotic zone will end up accumulating in the twilight zone, and that should actually increase the signal to noise ratio for biogeochemical variables. And I think with that, how am I going for time, Adrian?
You're okay for another minute.
Okay, so I'll just finish with this final slide, and that is a pretty obvious one, I suppose. I just wanted to say, well, some of you might be wondering, well, you know, do we have this is a pretty niche measurement. Do we have the measurements to actually detect changes? And the answer is that we do. We have these repeat hydrographic sections. Thanks to geotraces, we have and the efforts from various nitrogen labs around the world. We have repeat hydrographic sections of these of isotopes in the global ocean. I just highlighted where these changes, where these particular sections might be very useful to measure going forward in the coming decades. And so the repeat hydrographic sampling of these nitrogen isotopes in nitrate, not only are they practically detectable, they're also they're practically detectable in numerous ways, but they could supplement bioargo and satellite ocean color to track the changes in net power production going forward. And with that, I'll just leave it with this slide here. If you're interested, read the paper.
Excellent. Thank you very much, Piers. Fascinating stuff there. Let me throw it open for questions. So if anybody's got a question, either raise your hand, just speak, or put something in the chat. So I don't see anything yet, so maybe I get the ball rolling. So I'm trying to remember the figure that you showed from your model where you had the decrease in your delta 15N. So yes, that also showed a decrease in the Southern Ocean, which wasn't correlated with the decrease in primary productions. So is that sort of a co-effect with changes to iron as well?
I would say that change, because so we're talking about the figure, this figure here.
Is that the one? Yes, so I think that's the one. Yes, so if you look at that, then you've got a decrease in the bioavailable nitrogen in the Southern Ocean.
Yeah.
But you've got if I understand it, you've got an increase in the primary production.
Yes. 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 So the Southern Ocean is largely, there's lateral flow going on. So I think even though there's an increase in that primary production I would expect the signals of that change to be much greater deeper in the water column, because associated with mode water and intermediate waters, at least north of the polar front, and in the Southern Ocean, even though there's an increase in net primary production, that won't be felt in the Twilight Zone directly beneath the upwelling area. But that's why these signals in, say, the Southeast Pacific and in the Indian Ocean, in terms of the Jaya, are much less, they're not a decline they don't decline as strongly as the other regions, because of this influence of an increase in primary production, increase in the isotopes that is then subducted and then moved northward into the Jayas. Does that make sense?
Yes, I think so.
Yeah.
I always have to think about these three-dimensional things for a little while before they finally settle in. I can see that, so I've got two here now. So first, Ken, would you like to come in with a question?
Sure, thanks. Interesting model, and particularly that the Twilight Zone response is different. Maybe from what I got is that the noise is smaller. But if you project forward of climate, and is that connection purely physical in terms of downwelling mixing? If the connection between the euphotic zone and Twilight Zone is a biological carbon pump, it's sinking particles, do you assume that's fixed over this whole 100 years? Because that would also change as we alter temperatures and salinity and community structure in the surface, wouldn't it?
Yeah, absolutely. And of course it does. But the important thing, I think, for just getting away from the isotopes, I think registering that biogeochemical changes are going to be felt in the Twilight Zone, not only because of this physical mechanism, downwelling in, say, subtropical gyres, but also because of this vertical vector, which you're talking about. So I think that will be there regardless of whether that vector will still be net downward, regardless of what happens to changes in carbon export and the rate of organic matter sinking. And that is an important vector by which these signals are transferred downwards.
So I guess that downward flux is fixed in your model for those 100 years.
It does change. No, it definitely does change. Yeah. I can't tell you exactly by how much. All I know is that what I can say is that because nitrogen limitation is already it's already strong in these giant ecosystems, and net primary production is already quite low. The changes there are quite small. It's really what happens in the tropics that's most important for the signal. So if you think about a particle that upwells in the tropical oceans, and then where nitrogen is replete, that will then eventually travel into the some of those particles eventually travel into the subtropical gyres and then downwell into the twilight zone. Now, in a situation where you've made those tropical areas a little more nitrogen limited, you've shrunk that equatorial tongue away. That's when these signals when these changes to the isotope happen en route and then end up accumulating in the subtropical gyre. So it's not necessarily what happens directly above, but it's what happens en route to those water particles they move in. Yeah.
Thank you. So that sort of brings us to, we've still got time for one more question, I think. The question that John Dunn has. John, do you want to ask the question?
Yeah, so I just asked, what is the impact of nitrogen fixation on gyre Twilight Zone N15 in this model, and whether it's well constrained?
Yeah, so the nice thing about, I mean, well constrained is a interesting phrase there. So what do I want to do? Okay, I'll try and answer the question before I get distracted by a different slide. But as you know, John, the nitrogen fixes tend to provide, well, they provide nitrogen to the surface ocean, and this nitrogen that they fix tends to be low. They have a low isotopic value. So I guess, John, are you asking whether some of these signals could be due to nitrogen fixes?
Well, I'm just wondering if, how much variable nitrogen fixation with differing, phosphorus and iron limitation would come in to, to these signals.
Yeah, no, it's a good question. It's something that I did think about. I think I'll attack it with I'll answer it with two different points. I just want to show you a slide that I didn't include. I did some extra simulations where I pulled apart the effect of warming and circulation on these changes, and then looked at how the resultant field stacked up against the full model where both warming and circulation occurred. Warming being on microbial rates and circulation obviously on substrate supply. And then I looked at the correlation between those fields. So if you had, say, the circulation was most responsible for a change in the ocean, then the value, this bar would be close to 1. So for instance, here in a simulation where only circulation changes were occurring, which is in the black bar, the circulation changes are almost entirely responsible for the decline in nitrate in the surface ocean in this model, in these simulations, right? Same for the isotopes, and less so for nitrogen fixation. Nitrogen fixation tends to be affected by both substrate supply, as you say, phosphorus, but also warming. And so both of those things are important for the nitrogen fixation response. And yet we find that the response in the isotopes is almost completely due to changes in some of the circulation. And the other thing that I wanted to say about the nitrogen fixes is they're very, very poorly constrained. What is the plot? Okay, so this is really interesting, right? So nitrogen fixation as the response of nitrogen fixation going forward is a known unknown. These are divergent simulations from different models showing that it could increase or decrease. And this is CMIP5, and it doesn't improve with CMIP6. These are just 4 models that save nitrogen fixation output from the CMIP6 that I recently plotted up. Absolutely divergent. Like there's no confidence in nitrogen fixation trends going forward. So that's an interesting, it's interesting to look at.
Excellent. Thank you very much. I'm afraid we're going to have to draw a line under the questions there. So thank you once again, Pierce, and I'm sure Pierce would be happy to reply to any other questions that people may have if you want to contact him by email. So thank you again.